All right, so let's talk about surface integrals. So let's just do a little recap. So for Calc 1, we know that the fundamental theorem of calculus helps us find the area under a line segment. So this is something that has been beaten to us to death. So here's f of x. And if I want to find the area under this curve, right, I'm just going to take the line segment from A to B and find all of this area. And that's just our integral. That's the basic integral that we've been taught. We extended our idea of area under a line segment to an area under a parametrized curve. So now let's say if I have a function f of x comma y comma z, and we don't want to find the volume underneath this particular f of x comma y comma z, but instead we want to find the area underneath a line segment, not a line segment, underneath a curve, then we can definitely do that. So if you have a parametrized curve, so this function right here is a parametrized curve r of t, and it follows parametric equations x of t and y of t, then I can easily find that particular area using this formula, the line integral over this particular curve c. Okay, using this monster of a formula. Okay, now let's say, for example, instead this guy, right? Remember that this particular double integral, what it gives us is the volume underneath underneath f of x comma y. Okay, but it can also give the mass of the region D of a lamina with density of f of x comma y. So this integral right here, so let me make this yellow. So this integral right here can have two different meanings. So one of the first meanings is, again, let me just go ahead and draw a picture. So if you have a surface and you have a particular, if you want to go look at this region right here, one of the things that we can do is you can find the volume of this. So you can find all of that volume. So this integral itself can represent volume, or it can also represent mass. Okay, and the way that it can represent mass is that if f of x comma y is actually a density, and you have the same thing, some parametric curve like this, right? Maybe I should draw it in x and y. So if you have x and y, you have a very thin plate. So a very thin plate. And at each point, you know, you have a density, so this is a thin plate. Then you can actually calculate the mass of this guy. Okay. So this can be just either the mass of this particular thing, or it can also be the mass of a wire. So this can mean many different things depending on the context. Now let's say our region D is not flat. Okay, so this region particular D is not going to be flat. So now we're going to look at a surface, and now we're going to go into the 3D space like this. All right, so something like this. So what you can kind of think about this, okay, so this is surface S, okay? So our surface integral is defined to be the double integral over the surface S, so this is S, of f of x comma y z ds. So notice that there's a similarity here between this one and the line integral. Okay, so the line integral is right over here, right? S here is with respect to the length. Here, this S is with respect to the surface. Okay, so okay, so now S here is our non-flat surface. So this can be a little confusing. So if you kind of think about it geometrically, it doesn't quite make sense, because if you try to think about it, okay, well, here is a three-dimensional object, and we are looking for the area underneath that curve. So if you think about it in geometrically, you can think about, oh, this is a four-dimensional object. This is a 4D thing. And then we're trying to fit and then you got this volume over here trying to project it onto the 4D. That's just really confusing. What I think is easier to kind of think about is that imagine finding the mass of this surface with mass density f of x comma y comma z. So imagine that at every single point, x, y, and z, this surface is actually dense on certain parts. Maybe it's a little lighter on some other ones, maybe more dense in other parts. And that way, the density of this particular object can be described by this function. So think about that as density function. Don't think about it as geometrically what it looks like, because that can be really confusing. All right. So ds here would be the surface area of the surface. Okay. So if we look over there before in our curve, this s was the length. Okay. So we were cutting up each of these into little pieces and trying to find the area underneath this particular curve. Here, we're going to separate everything into patches. Okay, so we're going to take little patches, right, of surface and try to go ahead and integrate what that whole thing will be. Okay, so that's where this ds would look like. These ds is with respect to surface area. Now, if you remember from our previous chapter, our surface area formula was given to this. And if you remember correctly, this guy came from the fact that I want to find the surface area. And one of the things that we wanted to look at was we got the surface. We were going to look at one particular part, and we were going to approximate it with the tangent vector. With the tangent plane, I'm sorry. With the tangent plane. And in order for me to approximate it with the tangent plane, I was trying to find this area of this parallelogram, and the way that we found it was with a cross product. So we take this vector and this vector. So let's say you take the two vectors, v and u, and what we did, we took the cross product, and then we took the magnitude of it, right? So and then we took all of these guys, and then we ended up getting this surface area integral. So basically, this guy is actually going to be our ds. So our ds, this guy, our differential ds, is actually going to be this entire thing. Okay, so that's going to be our surface area, which is very analogous to our arc length formula. So plugging this into ds means that for z, I will have to plug in the our surface itself, right? Our surface integral, whatever this value, whatever this surface is, I'm going to plug it in, and then I'm going to go ahead and solve it. So here is basically the surface integral formula. So if you parametrize the surface z in terms of x and y, this is going to be our formula. So this is a basic parametrization. So if you look at our other parametrizations that we have here, if you have a surface that's parametrized this way, okay, where x equals x, y equals y, or z equals z, or all of them are interchanged, which is a basic one, then you're going to be able to find the surface integral using any of these formulas. Notice that here I switched it if it was oriented in a different direction. So these guys account for different orientations, but the formula themselves are the same. I just changed the partial derivatives. Now let's say, for example, this surface wasn't a very function-like surface around its axis. Instead, we have something like cylinders, cones, spheres, something like that. Well, if you have all of these other guys where the parametrization is not quite as nice, right? We're going to do exactly the same thing, but instead of using this surface area formula, we are going to go back to how we were calculating the area of the surface area of the surface by using its cross product. So that's why if the parametrization is unique, so like a cylinder, you have a cylinder or sphere or anything like that, then in that case, our surface area is going to be this guy. So we're going to go back to just the magnitude of the parametrization of the two curves, of the curve itself. Okay, so in this case, doing so, all we're going to do is that our surface integral is going to look like this. This is what our surface integral looks like. Okay, so they're kind of the same. It's just that one of this one's a lot harder because this one you have to do a cross product. So Let's hope that the problem will be given to you as a nice parameterization where you can just let x and y be the parameters and then z just plug in x and y. And hopefully it's not something horrific like a cone or something bad where you have to do a cross product. Okay. So let's go ahead and do an example. So let's evaluate the surface integral, x plus y plus z. So imagine that this is its density, ds, where s is the portion of the plane x plus 2y plus 4z equals 4 lying in the first octant. Okay. All right. So now this problem, let's go ahead and take a look at it. So let's figure out what exactly they're trying to solve. So if you think about x, y, and z, it's x, y, and z. What you really have is our density. So imagine this is our density function. So there's going to be some parts in it where it's a lot more dense, okay, than others. And let's go ahead and figure out the part of S. Okay, so this S. So this S is our surface x plus 2y plus 4z equals 4. So x plus 2y plus 4z equals 4. Let's find our, and we're looking at the first octant, so let's find our x-intercepts, y-intercepts, and z-intercepts. So you can see when y and z equals 0, you're just going to get x equals 4. So in x, you're going to go all the way up to 4. When you let x and y equal 0, you're going to see that 4z equals 4, so z equals 1. And then when you let y and z equal 0, you're going to see that x is just going to be equal to 4. No, wait, that's going to be, no, it's going to be, oh, no, I already did that one. I'm going to let x and z be 0. So you're going to get 2y equals 4, so y equals 2. Okay. So imagine that this is actually the portion of the plane that we're looking at. And this guy in the inside, x plus y plus z, is basically its density at every single point on this plane at the first octant. So imagine that we got all, like it's probably dense in some other places than it is in others. Okay. And what we really are doing, if we're taking the density and multiplying it by its area, we're actually calculating its mass, the mass of this triangular thing. Okay, so that's basically what we're calculating. So imagine that we're calculating the mass. That might help you visualize what exactly this is. Okay, now let's think about this. Is this a really nice parameterization? Yes, we can go ahead and make this into a nice parameterization. And let's solve for the value of z. Okay, so I'm going to have 4z equals negative x minus 2y plus 4 divided by 4. So you're going to get negative 1/4 x, negative 1/2 y, plus 1. All right. So this is going to be our plane, right? So this is our plane. So now let's parametrize our plane. Well, to parametrize it is pretty easy, right? We're not going to use the cross product because this is a really easy parameterization. We're just going to let x equal x, y equal y, and z equal this crazy thing. I'm going to write it as 1 minus 1/4 x minus 1/2 y. And that's why I have the negatives afterwards. So this is going to be my parameterization. You can also write it as r. So r of x comma y equals x, y, 1 minus 1/4 x minus 1/2 y. So we can do it that way. Now, typically, if you went ahead and made a mistake and did this formula, you would still get the same answer. You wouldn't do anything different. You would just do a little bit more work because you would have to calculate the cross product of this guy. But this other formula that we have up there, this one is already, the cross product has already been done. This is what the cross product is. So I'm going to go ahead and just grab this first formula. You can see that z is equal to a function of x and y, so it's better to use this one. And that's why I let z equal. If you did y equals, then you would use this formula. If you let x equal, then you would use this formula. So I'm going to use the first formula. So we're going to have, so now let's calculate our surface integral. So the surface integral of f of x comma y comma z ds is going to be equal to the double integral over the region D of f of x comma y. I'm going to plug in whatever y is in there. So I'm going to plug in g of x. Yeah, I'm just going to put g of x comma y square root of g sub x squared plus g sub y squared plus 1 dA. I'm just going to double check that I made the formulas right. Did I make the formulas right? Yes, okay. I thought I wrote f in there. Okay, so yes, g. Okay, and now let's just plug everything in there. So one of the things that we got to do is take our partial derivatives. So the first thing that I got to do is take the partial derivative with respect to x. Okay, so if I take this, so let's write it this way. So you might be wondering, what's g? This is going to be my g. So this function, this value z, is what my g is. So that means g sub x, if I take the partial derivative with respect to x, I get negative 1/4. Take the partial derivative with y, I'm going to get negative 1/2. So let's go ahead and plug everything in here. Okay, so there's a lot of things. So we got this x plus y plus z. Okay, so we got the x plus y plus z. So what is z equal to? So z is equal to this guy, the negative 1/4 minus 1/2 y plus 1. That's that guy. All right, so I'm going to put this in brackets. And square root, okay? So square root of g sub x, okay, so that's going to be negative 1/4 squared. G sub y, that's going to be negative 1/2 squared plus 1, okay, dA, okay? So I'm just going to not worry about the region just yet. All right, so now let's take a look at the region itself, okay? So the region, actually, let's go ahead and clean this up. It's better to just clean it up. So this is going to give me, what, 3/4 x, then 1/2 y, then plus 1. Here, I'm just going to get, so this is 1 over 16 plus 1 over 4 plus 1. So that's just going to give me square root 21 over 60. Oh gosh, let's see. So square root 21 over 16 dA. So I can do that. I'm going to take that out. So square root of 21 over 4, double integral over the region D, 3/4 x plus 1/2 y plus 1 dA. Okay, now let's look at the region D. So if we look at the plane, and let's look at the two-dimensional figure that we end up tracing. So that's going to be in the xy plane, so this guy. So in the xy plane, in the y direction, you're up 2, and in the x direction, you're over 4. So this equation of this line is going to be negative 1/2 x plus 2. Okay. So now I'm going to use a type 1 integral. So this is going to be square root of 21 over 4. This is going to be from 0 to negative 1/2 x plus 2, and then from 0 to 4 of 3/4 x plus 1/2 y plus 1 dy dx. Okay, and we've done these integrals many different times already. So I'll just go ahead and tell you the answer. It's going to be 7 square root of 21 over 3. Okay, and again, remember this is going to be mass of this particular surface. So you can see this problem incorporates a lot of different tools that we've learned in Calc 3. So this is a really good mastery problem to know if you really understand everything that's going on here.